Okay, so here we are in the Cirrus SR-22, a wonderful single-engine prop plane. I owned one for quite a few years. It's an absolute treat to fly. So we're going to go to engine specs, and we're doing the SFC tab. Okay, reciprocating engine SFC, specific fuel consumption. So this is the screen we're going to look at for a reciprocating engine airplane. And of course, I'll do all the tabs here in this video. But we're going to enter a high and a low altitude. Those are simply the high and low points altitude-wise for which we want to enter specific fuel consumption values. And actually we'll interpolate between those, of course, based on air density. And then you'll notice for the high and low altitude, we have the best power SFC. What is best power SFC? Well, in all these reciprocating engines, you've got a red knob that you can advance forward for maximum fuel flow or pull backwards for minimum fuel flow. And this is a fuel-air ratio. Okay, it's a ratio of fuel to air. And if you kind of advance it kind of near the full rich side, you get what's called your best power. That is where you get the most horsepower out of the engine. If you pull it back, you get your best efficiency. So you get the most horsepower per gallon per hour fuel flow. So at high altitude, we enter our high and low altitude best power SFC. This is the specific fuel consumption of the engine at the best power fuel air ratio at 12,000 feet and at sea level. And you'll notice it's basically the same. In other words, what this tells us is the altitude that the airplane's flying at has almost nothing to do with the efficiency of the engine. The engine gives the same horsepower per gallon per hour regardless of what altitude it's at. 0.458 plus or minus 0.001. And so what this number really means is if you take the horsepower and multiply it by pounds per horsepower hour, you will get fuel flow of pounds per hour. So if this airplane's running at 200 horsepower, multiply it by 0.459, you're obviously going to get about 190 pounds, or excuse me, about 95 pounds per hour. Divide that by about 7 pounds per gallon, and you're down to about 15 gallons per hour fuel flow, which is, of course, exactly what this airplane likes to burn. So down here at high and low altitude, best economy, now this is where we pull the red knob back until the engine is just barely running, and we're getting our most efficiency, our most horsepower per gallon per hour fuel. And you'll see instead of numbers of about 0.458, it's 0.408. In other words, it's a good solid 10% less fuel per horsepower generated. That's because we pulled the red knob back until we got our best economy specific fuel consumption. And again, the altitude, whether it's high or low altitude, makes no difference. Because these engines just, if they're at higher altitude, they have less air. And if they have less air, they make less power. But they also burn less fuel. The two counteract. The efficiency remains basically unchanged. Now, once these engines are down at idle, they're basically putting out no horsepower at all, so the game changes a little bit. We do idle fuel flow as a fraction of max static power. And so if this thing were to burn 25 gallons per hour at wide open throttle on the ground, maybe we idle at 2.5. So tweak these numbers to get the fuel burn you want in flight, both at low and high altitude, with the red knob forwards for max power or back for max economy. Set the idle fuel flow fraction to get your idle fuel flow where you want it to be. And then you have the full rich. That's a ratio. So here's the thing. When you have these Continentals and Lycomings, you can actually set them up, or the shop can set them up to burn more or less fuel. And if you enter 1.0 here, that just means it's as rich as a standard engine is called for by the factory. So I owned a couple of Columbia 400s in my life, and those things are turbocharged since they run a little hot from that turbocharger. And so they would actually enter more fuel than standard. They might have had like 1.5 here or something like that, or maybe it wasn't quite that bad. But they would actually burn more fuel than normal. Well, they wouldn't even burn it, but they'd send in more fuel than normal, and the fuel would evaporate and cool the engine. And so they actually used extra fuel for cooling. And boy, that is such a weak, pathetic little hack, isn't it? When you just have to say, our engine's running too hot, dump in fuel, we don't even burn, it'll evaporate and cool us down. I mean, that's pretty bad engineering. But that was the knee-jerk reaction they came up with, and it did let you run a turbocharged engine at 310 horsepower without overheating it, so I guess, it worked. But whenever I'd fly that airplane, I considered the full rich ratio at full power to be like an afterburner. As soon as I got the traffic pattern altitude, I'd reduce the throttle, go to my best economy mixture, and I'd even climb at best economy. And then I solved the fuel waste problem that way for almost the entire flight. So that is the reciprocating engine. Why don't we take a look at a turboprop next? So the Cirrus SR-22 is a really nice reciprocating engine airplane. Let's take a look at a nice turboprop airplane. My personal favorite, of course, Lancer Evolution. We go to engine specs, SFC. Now we're going to look at the turboprop tab, okay? High altitude for the turboprop is 28,000 feet, low altitude 8,500. Basically, this is as high as I'm going to fly. This is about as low as I can imagine flying, although really I don't even fly this low pretty much ever. Now, sure, we have our high and low altitude SFCs or specific fuel consumptions, but now rather than making the fuel mixture ratio be the deciding factor between the two numbers we want to enter, like you did the reciprocating engine, now it's percent NG. What's NG? NG is the gas generator RPM. It's how fast that little compressor inside the engine is spinning. Remember the way these turboprops work. A compressor compresses air. That compressed air has to escape the engine, and it escapes the engine by running through a little windmill on its way out. Lucky for us, that windmill is attached to a propeller, hence the propeller spins in this process and pulls the airplane forwards. That's how the turbine works in a Pratt & Whitney. And this engine only works right if that compressor is spinning at maximum RPM. If the compressor slows down, the engine just doesn't work right anymore. And so we've got a 95% compressor RPM, 95% NG, and an 80% compressor RPM. This is like a high power, 95% RPM. This is a low power, 80% RPM. And look at the difference in efficiency. Oh my God. Low altitude, 95% compressor RPM, specific fuel consumption 0.525. Now, as you may remember from that Cirrus, the specific fuel consumption of that airplane, what was that? 0.45? So the specific fuel consumption of the Cirrus is 0.45. The specific fuel consumption on the Lancer at 95% NG is like 0.52. It's hardly any worse. In other words, the Pratt & Whitney PT6 engine is basically just as efficient as a reciprocating engine. Isn't that awesome? It's just great. But there's a catch. As soon as that engine starts turning slower, the efficiency falls apart because the compressor ain't compressing the air anymore. So low altitude, 80% NG, 80% gas generator RPM. Our specific fuel consumption goes to 1.05, basically twice as much fuel per horsepower. So in other words, when you slow down a turboprop engine, and in particular Pratt & Whitney PT6, down to 80% RPM instead of 95% RPM, it burns twice the fuel per horsepower you put out. Put another way, you could put out half the horsepower and still burn the same fuel. Now, you reduce throttle by reducing fuel, so it can't be quite that bad, but at half the fuel, you get like a quarter of the horsepower. So the PT6, it is almost as efficient as a reciprocating engine here. It's 0.5 compared to 0.45 or so in the Cirrus. It's almost as efficient as a reciprocating engine, but only when it is spinning 100% RPM or close to it, in this case 95% RPM. As soon as that gas generator RPM slows down because you're into a low power setting, the pressures in the engine don't work right and it just turns into a piece of junk. So if you must fly a turbine engine, you better go high so you can spin it at 95% RPM all day long or 100% RPM to make it efficient. It has to be flown at wide open throttle to be efficient. If you try and slow down a turbine engine, the efficiency falls to pieces. And you can see that math here. Pounds per horsepower hour. Again, take the number of horsepower, multiply it by this constant, and you get the pounds per hour. Divide by about 7, and you get the gallons per hour. So treat these numbers to get the right gallons per hour or pounds per hour if that's how you measure it at fuel flow for your engine. Idle fuel flow is fraction of max static power, 0.275. You may remember the Cirrus had a 0.1 here. This thing is almost 3 times the fuel burn at idle compared to maximum. Again, because these turbine engines do not work right when they are spinning slow. They're absolute turbines. God, they're just things of beauty, they're so powerful and efficient and smooth and reliable, but only if they're spinning 100% RPM, so all those pressure games are being played properly. And here's why it is. Remember, with a reciprocating engine, the air is actually compressed when this piston is moving up and down in a cylinder. Does it matter how fast that piston is moving? No. The air gets compressed, the fuel gets added, it expands. It doesn't matter how fast this is happening. I mean, the engine can run this slow. I mean, it wouldn't matter. The same compression and expansion are all in play because the gas is in an enclosed space. Turbines don't have an enclosed space. That air just comes through and gets compressed, goes right out the back. You can look right through a jet engine and see it. Look at the jet engine of an airliner. You can see from the front right through the back. In other words, if a turbine is turning slowly, it ain't working right. It's not. If you turn a turbine slowly, it's not a turbine engine anymore. It's a chain link fence. It doesn't hold the air. It doesn't hold anything. A turbine has to spin at 100% RPM to work right. So if you must buy a turbine, operate it at full RPM. And the thing is, you cannot do that at low altitude or you'll over torque and over stress, everything. So you got to go up to the thin air to run at 100%. So that's why turbines have to run high and fast to do their jobs properly. Cool thing about airplane engines. All right, why don't we take a look at a jet engine now? And I will vote on the good old 737 for this presentation. Engine specs, SFC. So now we're at the right-hand tab here, jet engine SFC. So again, the name of the game when I wrote the system was to make it so you could enter the little fuel flow points in the envelope that you're actually likely to encounter on the airplane to really explore the envelope of fuel consumption for the engine. And so what we've done here, I'm going to start at the bottom, maybe oddly. We've got our takeoff Mach number, takeoff N1, and takeoff specific fuel consumption. 0.4 per hour? Per hour? Isn't that a weird unit? Well, if we have 10,000 pounds of thrust, multiply that by 0.4, and we will have 4,000 pounds per hour of fuel burn. And that's why you have that weird fuel units of per hour. You take the pounds of thrust, multiply it by the per hour as SFC, and you have pounds per hour of fuel burn. And it looks like we use 0.4 down here. What about climb? At a climb of 90% N1 and a Mach number of 0.28, I'm just, for the intermediate climb, of course, Mach number varies with climb. I'm just taking an intermediate point here. Our mid-climb SFC, also 0.4. Our fast cruise N1, fast cruise Mach. Our fast cruise SFC is 0.615. So if we have 10,000 pounds of thrust, it'll be 6,150 pounds per hour of fuel. And our slow cruise, if we slow it on down, maybe 75% N1, 50.57 Mach. Boy, that's slow for a 737. I don't think anyone's going to operate the airplane that slow. Then your cruise SFC goes down to 0.535. And then X-Plane will do this kind of cool interpolation. Boy, I played forever finding the right way to interpolate between all these three-dimensional data points. It's sort of like it's interpolating in three-dimensional space or something like that. But X-Plane interpolates between all these to give you the SFC at any given, or the fuel flow at any given point. And so you just adjust these numbers to get the fuel flow you want in the real airplane. Once you've entered the cruise and climb and takeoff N1 and Mach numbers. Idle fuel flow is a fraction of max static thrust, 0.065. Well, that's a pretty small number, right? After we saw 0.1 for the recips and 0.275 for the turbines, how do we idle at such a low fuel flow in this thing? Kind of flies in the face of everything I've said about turbines, right? Where they only work if they're going fast. Well, here's how the 737 gets this done. It only has this tiny little turbine in its core where the fuel goes. And the output from that turbine is what drives a gigantic fan. It's just like, remember the turboprop in my airplane, the compressor pressurizes the air. The pressurized air has to escape from the engine. It runs through a windmill on its way out, and the windmill is hooked to the prop. The 737 is exactly the same layout as my turboprop. That N2 is the compressor. It compresses the air. The air has to escape from the engine. It takes the easiest way out it can, which is out the back where the turbine is in the way of windmill. That windmill drives the fan. And in the 737 engine, they made that little turbine that takes the fuel so small that it is just a tiny little fraction of the total engine, and that's the only part they actually have to keep running at idle. At idle, if that big, huge fan up front is barely doing anything, if it's just kind of going like this, who cares? The engine's at idle. They don't need to do very much to keep that big fan running. That big fan can just kind of lazily, slowly turn. There's no insulating wall of air necessary for the fan. There's no fuel associated with the fan. It's just like a propeller, basically. There's hardly any difference. And so that big fan can idle just as slow as you please. The only part they have to keep moving fast is that little turbine to keep the insulating wall of air built up, but the turbine is small. And so because of that, these big high bypass jet engines can idle at very, very low fuel flows and very, very low power outputs, which is awfully nice from an efficiency standpoint for the taxi and approach and landing phase of flight. Afterburner SFC, I would encourage you to put an afterburner on your 737 if you feel like it. That's here in the engines tab, afterburner thrust increase. Why not? It's a simulator. You can do it. And then your SFC here, which might be 3 or something like that. It's very, very steep fuel flow. So those are the specific fuel consumption numbers for the jet engines. And hopefully I've explained them all and you understand some interesting things about reciprocating engines where you adjust the fuel-air ratio for best power, best economy. Turboprop engines needing to run at a high RPM and having better SFC at a high RPM and worse SFC at a low RPM of the gas generator. And jet engines seeing different fuel consumption based on their N1, how fast their fans are turning, and their Mach number. Electric motors, you can see that for yourself. I don't need to explain it.